A great day to everyone. This is Dr. Cabrera again. I'll be giving a lecture on physiology for first-year medical students. And my lecture for today is the role of the kidneys in the regulation of acid-base balance. Before we start the lecture, let's pray that God will help you to understand what will be imparted to you today. Guide and enlighten you with this topic, which will add to the knowledge that you need to become great physicians, whom God constantly molds for the life of service and healing. Always ask this through blessings to Christ our Lord. Amen. Today's lessons will be quite challenging. It's long and it's quite complicated, especially those who have challenges understanding physiology and the cellular mechanisms and molecular mechanisms. So to help us at least understand it, so we should affirm, always believe, tell to yourself that I believe today's learning is fun, it should be easy and interesting, believe that you'll understand the lesson, believe that you'll pass the exams. And to start, we talk about the pH or negative logarithm. Always remember that the extracellular fluid pH range would be from 7.35 to 7.45, and the intracellular fluid inside the cell, the pH range will be from 7.1 to 7.2. Always remember that any substance that adds hydrogen to the body fluids are called your acids, and alkali are any substance that removes hydrogen from the body fluids. Generally, the concentration of hydrogen in the body fluid is low in comparison with other ions. Virtually all cellular, tissue, and organ processes are very sensitive to pH. Life cannot exist outside the range of the body fluid pH, which is from 6.8 to 7.8. Thus, we cannot survive with a pH of less than 6.8 or more than 7.8. Now let's talk about the bicarbonate buffer system. Bicarbonate buffer system is an important buffer for the extracellular fluid. The normal concentration of your bicarbonate will range from 23 to 25 milliequivalents per liter. A 70 kilogram individual can have at least 14 liters of bicarbonate in their blood. Your bicarbonate buffer system is regulated by both your lungs and the kidneys. So this below is the reaction for the hydration and dehydration of your carbon dioxide. So carbon dioxide is added with water, resulting to carbonic acid. And this reaction is called your first reaction, and it is very slow. That's why this reaction is the rate limiting step. While with your carbonic acid, it undergoes a very fast reaction. It's a brief ionization of your carbonic acid to become hydrogen and bicarbonate. It's very instantaneous. So your extracellular fluid can potentially buffer around 350 milliequivalent of hydrogen. Now, the amount of our carbon dioxide is determined from the partial pressure of carbon dioxide and its solubility in a solution. Okay, and we use your Henderson-Hasselbalch equation to quantitate how changes in your carbon dioxide and bicarbonate can affect the level of your pH. So we have your pH is equivalent to pK plus the logarithm of bicarbonate over the alpha or solubility of your partial pressure of your carbon dioxide. So it just means that the Henderson-Hasselbalch equation simply says to us that any changes in the level of your carbon dioxide or your bicarbonate can greatly affect the level of your pH. Okay? So that's the summary of your Henderson-Hasselbalch reaction. So any disturbance in the acid-base balance can result from the change from the bicarbonate are termed as metabolic acid-base disorder, whereas those resulting from the change in your PCO2 are termed as respiratory acid-base disorder. So again, any changes in your bicarbonate are called your metabolic acid-base disorder, and any change in your PCO2 are termed as your respiratory acid-base disorder. Now let's talk about the regulation. Okay, so hopefully you can appreciate this one. So this is our kidney, and our kidney will usually regulate the bicarbonate. And the lungs will usually regulate the carbon dioxide. The regulation of your acid-base balance are influenced by the amount of acid or alkali ingested and the amount of acid or alkali produced by cellular mechanism, thus, and the amount of excretion of acid and alkali by the kidney. So, again, the diet of humans and cellular metabolism produces acidic or alkaline substances, and alkali is normally lost each day through the feces, which will have a net effect of the addition of acid to the body fluids. Acid-base balance to be maintained acid must be excreted from the body at a rate that is equivalent to its addition. You have to note that if the excretion will be greater than the addition of acid, it results to alkalosis, wherein if the addition of acid is greater than the excretion, it results to acidosis. We should remember that carbon dioxide is usually termed as volatile acids because it has the potential to generate hydrogen ion after hydration with water. The substance acid is not derived directly from the hydration of CO2 is termed as non-volatile acid, an example of which would be your lactic acid, and it will have we'll learn later on of the clinical significance of such process. The clinics, in the event that there is normal insulin, wherein the metabolism of carbohydrate and fats are good, they are completely metabolized and they will just produce carbon dioxide and water. But in conditions where there is low insulin, either by resistance, insensitivity, or incapacity of the pancreatic beta cells to produce insulin, there will be a state of high glucose content in the blood termed as your hyperglycemia. If this goes on, the carbohydrates and excessive carbohydrates are then metabolized to several organic acids, like your organic keto acids, especially your beta hydroxybutyric acid. And this will now, too much of this will bring about the state of acidosis. So with low insulin, you can have your diabetic ketoacidosis. Okay. For hypoxia, for whatever reason, it's either the limitation of oxygen delivery, no oxygen at all, like in strangulation, or in oxygen delivery, like decrease in blood pressure, okay? Decrease in blood pressure, like in dehydration, your circulatory collapse. The body will be shifting from aerobic to anaerobic metabolism, thus producing a lot of organic acid, like especially your lactic acid. And accumulation of your lactic acid will bring about acidosis. So the treatment would be, for low insulin, you give insulin, or you improve the sensitivity of insulin, or you help the body recognize the insulin. Okay, so that's one of the treatment. And next would be just a very good oxygenation. Okay, this is a good cartoon. I'm a low carb diet person. Whenever I feel low, I eat carbs. Okay. Okay. So the net excretion of acid by the kidney will excrete an amount of acid equivalent to the production of your non-volatile acid. Again, your non-volatile acid are those acids not coming from carbon dioxide, addition of carbon dioxide and water, okay, and which leads to the replenishment of your bicarbonate through the neutralization of these non-volatile acids. So your net acid excretion must prevent the loss of bicarbonate in the urine. Most secreted hydrogen serves to reabsorb the filtered load of your bicarbonate. A level of 50 to 100 milliequivalent of hydrogen coming from non-volatile acid is produced and is excreted in the urine. That's why we have acidic urine. Okay, that's why you'll see one of the normal characteristic of urine is to be acidic. Okay, because 50 to 100 milliequivalents of hydrogen are normally excreted in the urine. Those are all coming from non-volatile acid. Thus, the action of the kidney is very important because the filtered load of your bicarbonate is approximately 4,390 equivalent of hydrogen are filtered into the tubular fluid. The urine, the kidney cannot excrete a urine that is really have a pH of less than 4 because the urine pH can only can tolerate from the pH of 4 to 4.5. For sufficient excretion, kidneys secrete hydrogen with urinary buffers such as your phosphate or creatinine. Between the two is the phosphate, which is more important. These urinary buffers are collectively known as titrable acids. So titrable acids, wherein you just take a determined by taking a sample of urine, then you put on alkali so that the urine pH will be equal with your plasma pH. That's why it's called your titrable acids. The synthesis and excretion of ammonia plays an important role in the acid-base balance because each molecule of ammonia excreted in the urine will mean there will be a return of one bicarbonate to the systemic circulation, in which this bicarbonate will replenish the bicarbonate loss during the neutralization of the non-volatile acids. Now, for the net acid excretion, or NAE, so this is the overall process wherein the kidneys contribute to the acid-base balance by absorbing the filtered load of bicarbonate and excreting an amount of acid equivalent to the amount of non-volatile acid produced daily. This table and the following other tables will show us the factors regulating the secretion of hydrogen or the reabsorption of bicarbonate by the nephron. So there are factors that can increase the hydrogen secretion, and there's the primary site of its action. For the primary causes, in response to the decrease in extracellular fluid, the effect of the secretion and reabsorption will be on the entire nephron. So as with the increase in arterial PCO2 with the entire nephron, cortisol will stimulate the proximal tubule for hydrogen secretion, and so as with the hormone endothelin, which is found in the endothelial lining, will influence the excessive influence on the proximal tubule. Now for the secondary factors, increasing the filtered load of your bicarbonate will have an effect on the proximal tubule. Extracellular fluid contraction will exert its effect on the proximal tubule, while the presence of your angiotensin II enzyme will be affecting your proximal and distal tubule. The aldosterone hormone will be affecting the distal and collecting duct. The condition of hypokalemia will stimulate the secretion of hydrogen in the proximal tubule, so as with the chronic state of parathyroidism, wherein increased level of your parathyroid hormone will influence the secretion in your thick ascending limb and your distal tubule. However, the above tables are due to the increased hydrogen secretion, and there are also factors that will tend to decrease your hydrogen secretion. The primary factors would be an increase in GCF, so it's the opposite of the increase in hydrogen secretion. So this one will bring about decrease in hydrogen secretion in the proximal tubule. Decrease in the filtered load of your bicarbonate will decrease the secretion in the proximal tubule. Your ECF volume expansion will decrease in the proximal tubule. The state of hypoaldosteronism will decrease the secretion in the distal tubule and collecting duct. Condition of hyperkalemia and acute state of parathyroid hormone increased levels will influence the decrease of secretion in the proximal tubule. This slide shows mechanism for the reabsorption and secretion of the bicarbonate by the intercalated cells of the collecting duct. For your orientation, this is the tubular fluid, and this is the blood. Okay, so in this one, this is your intercalated cells, and you can see what's important. There is secretion of your hydrogen to the tubular fluid and absorption of your bicarbonate to the blood. So what's also important is that we differentiate the two intercalated cells in the collecting duct. Your alpha intercalated cells will secrete hydrogen and absorb bicarbonate, while your beta intercalated cell will secrete bicarbonate rather than hydrogen in the tubular fluid. Now, this slide shows us the production, secretion, and transport of ammonium. Okay, so it's quite a busy slide. Okay, so the ammonium is produced in the cells of your proximal tubule, okay, in the term called your ammoniogenesis. Then ammonium is secreted in the lumen, and bicarbonate enters the blood. There's it in the lumen, and bicarbonate enters the blood. Okay. The secreted ammonium is reabsorbed in the Henle loop, especially in the thick ascending limb. Goes back. So goes in, goes back, and accumulates in the medullary interstitium. And then Ammonium is secreted by the collecting duct via the non-ionic diffusion and the diffusion trapping, as well as by the ammonium transporters. Both secretory processes require secretion of hydrogen by the collecting duct, for each molecule of ammonium excreted in the urines, molecule of ammonium excreted in the urine, a molecule of a new bicarbonate is added back to the extracellular fluid. So this is what ammonium is produced in the term of ammoniogenesis, goes into the lumen, then it is secreted and goes again to the collecting duct, goes out and excreted, and for every amount of molecule of ammonium produced, a new molecule of bicarbonate goes to the extracellular fluid. So for the ammonium system, any alteration in the pH of the extracellular fluid can affect and alter the intracellular pH. For example would be like in acidosis. So the changes will affect glutamine metabolism in the cells of the proximal tubule. In the event of increased levels of cortisol in response to acidosis, this cortisol stimulates ammonogenesis in the proximal tubules. And in the end, there will be an increased levels of ammonium produced, secreted, and excreted. Thus, there will be enhanced production of your new bicarbonate in the event of acidosis. So that's how the renal ammonium system reacts to the levels of acidosis. First, there's alteration of pH. There will be decrease in the intracellular pH. In response, there will be an increase in the cortisol level. Increase in the cortisol level stimulates the increase, process of your ammoniogenesis, producing large amount of ammonium, and it will be secreted and excreted, and for every molecule of ammonium produced, there will be a production of new bicarbonate going to the systemic circulation. Now let's talk about an ion gap. So in general, the sum of an ion and cation should always be equal. It's noteworthy to know that sodium and potassium are the predominant cations that makes up around 95%, and your chloride and bicarbonate accounts for 68% of an ion. There is always a difference between measured anion and cation. The unmeasured anions constitute what we call the anion gap. These are proteins. They are protein anions, sulfates, phosphates, and organic acid. So this is the formula for the anion gap. It can be calculated as the sum of your sodium plus potassium less the sum of your bicarbonate and your chloride. High anion gap acidosis are usually found in situations of renal failure and diabetes, while in cases of diarrhea, there is usually a normal anion gap acidosis. Again, high anion gap acidosis are found in renal failure and diabetes, while normal anion gap acidosis is found in diarrhea. That's how you differentiate different acidosis using your anion gas. For renal tubular acidosis, in this situation, the net acid secretion by the kidneys is impaired. The kidneys are unable to excrete sufficient amount of net acid to balance non-volatile acid production. And your renal tubular acidosis, or your RTA, commonly called your RTA, is caused by hydrogen secretion defect in the proximal tubule or the distal tubule, or due to inadequate production of your ammonium, like in cases of your hereditary and acquired conditions like your cystinosis and Fanconi syndrome. So these are the conditions wherein you can have renal tubular acidosis or RTA. So we have another term, your PRTA, or your proximal renal tubular acidosis. This is a autosomal recessive type of condition, and there is a defect in your sodium bicarbonate symporter, and even with the lack of your carbonic anhydrase. Another common condition would be your distal RTA, or distal renal tubular acidosis. So this condition can be caused by hereditary, by reaction to drugs, or urinary obstructions. For your hereditary and acquired conditions like your medullary sponge, in some patients with condition of Sjogren's condition, which is an autosomal, it presents with an autosomal disease, distal RTA, and results from antibody which is directed against your age ATPase. With your amphotericin B, the hydrogen secretion by the distal tubule and collecting ducts may be normal, but the permeability of the cells to hydrogen is increased. So for the buffers, buffers are solutions which resist any change of pH, and there are two types, your bicarbonate buffer and your acetate buffer. The buffering capacity of a buffer is equivalent to the ability of the buffer to resist change in pH when an acid or base is added. Again, physiologic conditions, the body produces more acid than bases because acid can come from food. Acids are produced by the metabolism of our lipids and proteins, and even of our carbohydrates. Produces for lipids and proteins, produces sulfuric, phosphoric, and organic acid. Cellular metabolism produces your carbon dioxide, and again with the was discussed earlier, and it will undergo slow and fast metabolism, like the hydration and the hydrogenation of your carbon dioxide to produce your carbonic acid, and then later on this carbonic acid will be metabolized to produce your hydrogen and your bicarbonate. Again, so this is a very important slide in the use of your buffer system in maintaining the acid-base balance. So we have two lines of defenses. The first line would be with your chemical buffer system, and it includes your bicarbonate buffer, your phosphate buffer, and your protein buffer system. While the second line of defense against any pH shift will be your physiologic buffers like respiratory mechanism. If there is too much hydrogen in acidosis, your lung will tend to increase its rate of exchange just to blow off excess carbon dioxide, or the renal system, which is the slower one, would be the to produce more bicarbonate by increasing more hydrogen. So for the control of acids again, in review, so control acids through the buffers. So buffer systems takes up hydrogen or release hydrogen as conditions change. Buffer pairs are weak acid and a base. And there's exchange of a strong acid or base for a weak one, which results in much smaller pH change. For the bicarbonate buffer, we have two buffers in this system. So we can have your sodium bicarbonate and your carbonic acid buffers. So the buffer system of bicarbonate buffer accounts around 65% of the plasma buffering capacity. And you have the phosphate buffer, which is the major intracellular buffer. For the protein buffers, it includes hemoglobin, and this buffer works in the blood. The carboxyl group gives up hydrogen ion, and the amino group accepts hydrogen ion. That's how they either take it or give it away. The side chains that can buffer hydrogen are present on 27 amino acids of your protein buffers and your hemoglobin. So this is just a trivia. So since I've told you that acids are also produced from the food intake, so this is just a list. In the food intake, water being at 7 and the soda being at 2. So the more acidic your food that you take in, the more hydrogen ion that will produce. PCO2 should be given up, and bicarbonate should be reabsorbed or produced in the systems by the kidney. That's how they. So we do not die, of course. We do not die unless you have problems with your kidney now. Your kidney will not be able to buffer everything because your kidney will be the last line of defense for buffering such possible changes in the pH. What about by your food intake? Okay, so for the acid-base regulation, respiratory regulation of pH, hemoglobin is a buffer. The nitrogen of imidazole can either give or accept hydrogen depending on the pH of the environment or of the medium. The pK of hemoglobin is dependent upon oxygenation. Oxygenated hemoglobin will give away hydrogen because it's a stronger acid, while deoxyhemoglobin will take a proton. pH influences oxygenation of hemoglobin in the lungs and the oxygenation of the tissues because acidity of the medium favors delivery, so they give up your oxygen. So in areas where there is an acidic medium, hemoglobin will tend to give away its oxygen. Alkalinity favors oxygenation. The generation of bicarbonate by RBC. The RBC absorb carbon dioxide, and this carbon dioxide is hydrogenated with water by carbonic anhydrase, producing the carbonic acid, and this carbonic acid will be dehydrogenated, okay, releasing the bicarbonate in the plasma. Thus, there should be a bicarbonate carbonic acid ratio. So we have the pH should be at 7.35 to 7.45. Okay. An increase in pH, okay, for the if okay, for some factors, okay, it can cause hypoventilation or hyperventilation in the lungs. Hyperventilation will tend to increase pH by releasing carbon dioxide. This now entails the formation of an alkalotic environment. This will trigger the lungs to hypoventilate as a compensation and conserves carbon dioxide and decreases the pH and try to go to the normal pH. Same with your hypoventilation. The hypoventilation will conserve carbon dioxide, and this will decrease your pH, brings about an acidic environment, and it will trigger a compensation, and the lungs will hyperventilate and increase the loss of carbon dioxide, thus increasing the pH. We'll try to maintain the normal pH range of 7.35 to 7.45. The renal mechanism for regulation of your acid-base balance. Usually the buffer systems of first-lines are temporary solutions. The secondary will be your respiratory mechanism, but provides a short time of regulation, while the permanent solution will be on your renal mechanism. The renal mechanism will eliminate non-volatile acid buffered by the cation, especially your sodium. Usually your renal mechanism will try to maintain abundant of your alkali reservoir or your bicarbonate. So there are 4 types of primary acid-base disorders. So we have your respiratory. It can either be acidosis or alkalosis. Metabolic, it can either be acidosis or alkalosis. So you can see, so respiratory, always think of your carbon dioxide, or always think of your respiratory. If there's increase in your PCO2 levels in the ABG, think of respiratory acidosis. If there's increase, that can be respiratory alkalosis. So as with the decrease in your bicarbonate, will mean metabolic acidosis, and increase in your bicarbonate will mean metabolic acidosis. Okay, so when you see respiratory, think of PCO2. When you see metabolic, think of your bicarbonate. Always think of your Henderson-Hasselbach equation. Okay, so that's it. My reference is the 6th edition of the Vernon-Levy. Hopefully you understood something. It's just, in essence, our kidneys are the last line of defense in the acid-base balance. Okay, there are a lot of buffers and balances just to maintain the pH, plasma pH of 7.35 to 7.45. In the event of there will be imbalances, compensations and defenses will come in. Initially, you have your buffer system in your plasma. Later on, it will entail your respiratory involvement, which is actually is faster, but it is only temporary. And the final regulation would be of your kidney. So as possible, take care of your kidneys, because losing that kidney could put you in a very unbalanced condition. So thank you. So hopefully this will be posted in my YouTube channel. Just click and subscribe so that you'll know whenever I have new lectures posted in the channel. So thank you very much.